Remember being a kid on a seesaw? If you were stuck at the top while the bigger kids sat on the ground, you already understand the core physics of one of the world's most complex transportation systems. Now imagine taking that exact same seesaw, removing the playground dirt beneath it, and dropping it into a giant pool of water. If you scale that wooden plank up to the length of a skyscraper and swap the timber for tens of thousands of tons of steel, you have a modern cargo ship. Even with a displacement of 100,000 tons, the vessel is governed by the exact same physical balancing rules as that simple children's toy. In the maritime world, the balance of this giant floating seesaw is called trim. Trim is the difference between how deep the front of the ship sits in the water compared to the back. To measure that balance, sailors look at the draft marks painted on the hull. The front end of the ship is called forward, and the back end is called aft. Looking at this slide, if the forward draft is steeper, the vessel is trimming by the bow. If the back sits deeper, it's trimming by the stern. When the difference is zero, the ship is on an even keel. Keeping the ship on an even keel is a daily obsession for the crew. Without that precise balance, the hull drags through the water, wasting fuel and compromising steering control. Every seesaw needs a fulcrum, a hinge to pivot on. On a ship, this invisible hinge is called the center of flotation, often abbreviated as LCF or simply the letter F. Imagine a port crane locks onto a massive 60-ton shipping container sitting right at the forward edge of the deck. The crane lifts the container, carries it through the air, and sets it down near the back of the vessel. Here we see a diagram of that exact process. As the weight, labeled W, is shifted a distance, labeled D, the entire ship physically rotates around the center of flotation, marked with the red F. The bow rises, and the stern sinks. Shifting cargo like this keeps the total mass of the ship the same. The vessel displaces the exact same amount of water, but the redistributed load completely alters the angle of the tilt. How does the ship react when a crane lifts a massive weight from the dock and lowers it onto the deck? Adding new cargo triggers a two-step physical reaction. First, the entire ship becomes heavier. This document shows the first step of the calculation, parallel sinkage. The new mass pushes the entire hull straight down. Because the container is rarely placed dead center, the ship immediately undergoes step 2. The off-center weight forces the hull to tip, changing the trim. Calculating this sequence, downward sinkage followed by the angle tilt, is a mandatory routine. Officers must run these numbers to guarantee the ship's final draft stays within the safe depths of the harbor. As the hull tries to tilt, the ocean pushes back. This means different hull shapes offer different levels of resistance or stiffness against tipping. A wide, flat cargo barge requires a massive amount of force to tilt, whereas a narrow speedboat dips its nose with just a slight shift in passenger weight. To measure this resistance, naval architects use a specific metric called MCTC, which stands for Moment to Change Trim by 1 centimeter. This slide details the formula to find it, involving the vessel's displacement, its metacentric height, and its total length. By knowing the MCTC, a captain can mathematically predict exactly how many centimeters the hull will tilt before a single container even leaves the dock. When these calculations are ignored, the physical dangers are severe. A ship heavily trimmed by the head plows its bow deep into oncoming waves, taking tons of crushing water directly over the front deck. Trimming too far by the stern presents its own hazards. The elevated bow catches the wind like a giant sail, throwing the ship off course. The absolute failure state happens when the tilt is so extreme that the rear of the ship lifts out of the ocean. The propeller, designed to push dense water, ends up spinning uselessly in thin air. Poorly managed trim represents a catastrophic safety failure that can physically cripple a vessel in the open ocean. When you watch a fully loaded cargo ship glide smoothly into port, resting perfectly level in the water, you are watching a feat of invisible physics in action. That perfect even keel is the result of officers using math to master the balance of the heaviest, highest-stakes seesaw on Earth.